Welcome to this next video for Module 3B of MCT 450 Advanced Mechanics. In this video, we will cover deflection, torsional stresses, and combined stresses. When a transverse load is applied to a beam, internal stress is not the only result. There is also deflection of the body in relation to the supports. Recall that based on Hooke's law, the stress, strain, and elongation are all related factors. Provided the load does not exceed the material's elastic limit, the beam will deflect when the load is applied and then return to its original shape when the load is removed. When the bending moment is known, the deflection can be calculated by means of double integration of the moment formula. The resulting formula is specific to each type of beam support and load setup. Thus, you will typically look up the deflection formula in beam tables rather than performing the double integration. In some cases, the textbook provides maximum deflection formulas for specific beam setups. In other cases, it does not give you the fully derived formula, but rather a singularity function to get you partway along in the derivation. Be careful you do not confuse the singularity function with algebraic functions. The singularity functions are denoted by the somewhat funky singularity brackets around the function. These singularity functions allow you to skip portions of the double integration, making your work a little bit quicker. This slide provides more information on singularity functions. There are links provided if you would like to see a complete example of singularity functions. You will not be required to use them for this course. The formulas shown here provide an algebraic means to calculate the maximum deflection for various beam setups. While deflection and stress are related, for determining design safety, we are usually more interested in stress. Deflection becomes a point of interest when we need to confirm that the loaded system will not create an interference or otherwise violate some stated code. When we consider beam applications, the stresses that can occur are based on the different types of loading. They include direct axial stress, bending stress, transverse shear stress, and torsional shear stress. We will now take a deeper look at torsional stresses. First, we need to define the polar moment of inertia. This is a geometric property of a given cross-sectional shape and size to resist twisting about the beam's longitudinal axis. This property is related to the second area moment of inertia and has the same units. The tables shown provides derived polar moments of inertia for common cross-sectional shapes. It also can be derived through integration with respect to the area. For cylindrical beams, the torsional shear stress is the torque times the radius divided by the polar moment of inertia. You can also determine the angular deflection or twist that will occur due to a given applied torsional load. The FE exam reference handbook provides polar moments of inertia equations based on the cylinder's radius. I prefer using the diameter in my calculations, and thus here are some formulas in this regard. It doesn't matter which version you use, you will get the same answer. If you have a beam that's subjected to torsion with a non-circular cross-section, a different stress formula must be derived from the basic formula T divided by Q. In this equation, the variable Q is a factor related to cross-sectional area, but it is not the same as the first area moment that we used for the transverse shear equations. These tables from our textbook provide information on how to derive Q in order to find the torsional shear stress equation. The tables here are from an online source that has completed the work of defining the torsional shear stress formulas for various common cross sections. When analyzing a loaded beam system, we must first determine the applied stresses. The four possible stresses, again, are axial stress on the ends of the beam, bending stress, transverse shear stress, and torsional shear stress. Once these stresses are known, the next step is to apply them to your stress elements taken at each point of interest. The axial and bending stresses are considered to be normal stresses. Then they would be applied to the three axes, X, Y, or Z, on your stress element. Transverse shear stress and torsional shear stress, by nature of their names, are both shear stresses and apply at a given planar face, such as the XY, XZ, or YZ planes. Generally, there are two locations on the beam where we need to consider the applied stresses and create stress elements for those locations. Consider the cantilever beam shown here. If we take a cross-section at the point of maximum stress, there are a few key locations to consider. I have superimposed a clock face on the cross-section to help identify these locations. One stress element should be taken for either the 12 o'clock or 6 o'clock position. These locations are where the bending stress is maximum for this setup. However, shear stress is 0 at these locations. The 3 o'clock and 9 o'clock positions are where the shear stress is maximum, but bending stress is 0. So one of these two locations should be studied as well. In a case like this one, with only one applied load, it does not matter which of the two locations are used, their magnitude will be equal. Other setups may cause one option to be better than the other. If torsional shear were present, it would be the same at each location of interest. Generally, the torsional shear stress and the transverse shear stress can be added together at locations where both are present. That's it for this video. Thank you for watching.